Welcome to CQS seminar. Today's speaker is Professor Bum-Hoon Lee. He will give a talk about early dark energy for observing cosmic birefringence and the Hubble tension. Please.
Thank you. By the way, is it possible to get rid of this one, or this is impossible to? So that okay, so the like many people here, my main interest nowadays is in gravity and cosmology, and trying to understand actually some gravity model through which I can understand cosmology better, especially through the collaboration with the phenomenology, dark matter, and cosmology group here led by Stefano. So here, to really give some insight to those who are experts in gravity, I'd like to introduce more cosmology-oriented problems that I dealt with rather recently, and so that you can think about some many gravity models and apply to these kind of problems. That's the main reason why I decided to give a talk. Okay. Yeah. So the okay. 야, 페이지 다운 이걸 해. 이걸 So I'd like to first after some motivation, I'd like to introduce you what is the early dark energy, and then show you how it will resolve the some problems in cosmology. Okay, as a motivation. Our question is whether Einstein gravity is still really satisfactory. If you are theorist, as it is all theorists, then the present point of view of the theory is that every field theory should be understood as an effective theory. Then that means it is quite well known that the Einstein gravity theory, if we just go higher and the higher energy scale, it is kind of sick. It's a little bit, it's not well defined. So if we have some UV complete theory like a string theory, and take a low energy limit to understand low energy as following the effective theory aspect, then Einstein gravity is nothing but the first order linear term. And there must be higher orders. So in other words, if as a theorist, I believe Einstein gravity theory works well practically, but it cannot be the fundamental theory. There must be some corrections. That's, as a theorist, I was taught that way. Now, I think some motivation that we have to go somewhat beyond Einstein gravity from the observational aspect. And the answer is that at least there seems to be some signals. For example, for the Hubble tangent, if we measure Hubble tangent based on the whole universe signal from the CMB right after the combination, that's a blue-colored one. And by looking at the somewhat supernova or supernova type 1 near us, then if you see until, let's say, 2013 or something, what is the conclusion we can have? Well, so with the error bar large, you may say that blue color value and the red color value should be consistent. However, after 2012 or 13, each measurement became much more precise, so that not only the mean value, but also the error bars are reduced. So they are quite different. How much different? About 5 sigma away. So there must be something wrong it may be in the measurement or it may be in the fundamental level of theory. Something is wrong. Something is very strange.
By the way, if you look at this plot, and just considering it now, you see that there seems to be a discontinuity in the CMB measurements.
In the CMB measurement,
Up to 2013, there was some kind of range, and then suddenly there is a drop. So
okay.
this means that there has to be some systematics.
Okay, so let me just first jump to there here. So there are many types of WMAP data, then the Planck data. So there must be some systematics, and which one is
In
better.
other words, the WMAP and the
This WMAP and the Planck.
and Planck are not consistent with each other.
I see. You want to say that? I see.
Simply because if you look at the arrow bars, the measurement of 2020 and the measurement 2010
Yeah, but
are not
so
compatible with each other.
within 1 sigma.
Yes,
right?
within 1 sigma.
Yeah. So okay, that's also a good point. But okay. So another example is so-called cosmic birefringence. Birefringence is 복굴절. So that means some material effect. So right-handed polarization and the left-handed polarization propagate a different speed. Then in terms of linear polarization, which is the sum of the right-handed polarization plus left-handed, since they are propagating different speed, the linear polarization plane will be rotating. And to explain that, you do need parity violation. Without that, you cannot explain. Okay? So rather recently, the rotation angle, so far it was consistent with 0, people thought, but now it is non-zero. As you see here, it is non-zero value with some sigma. So to put it another way, you may say that non-rotation or parity invariant theory will be ruled out at the 3.6 sigma level. That's what some people argue. So still, unless the statistics is up until some 6 sigma or something, it can be just disappearing as a statistical things. But so still it's a very suggestive, something is suggesting. So if we accept this, and there are some other observations, but I will focus only those two, Hubble tangent and also this cosmic birefringence. How to resolve? Then somehow we have to go beyond Einstein or go beyond lambda CDM, because the lambda CDM is based on the Einstein gravity, and that one cannot explain these kind of things. So we should go beyond that standard picture. How do you go there? So we can just follow some logic, but it is critical, it is essential that we have to introduce some additional degree of freedom. For example, higher curvature terms or scalar fields or some other things. So I have been working on this higher curvature terms, especially with Stefano group. We are doing something here. But today's the seminar will be mainly for the scalar field, adding some scalar field, and just following based on the Einstein gravity. We do not touch metric. We just think about this scalar field effects. Okay. So here along the evolution, important thing is that there is in the radiation dominated one in the whole universe, will be eventually the energy portion will be slower, and so matter will be there's after some stage matter will start dominating because radiation drops faster than matter energy density. And during some matter dominant era, there is a so-called recombination where the plasma state, proton and the electron will combine to the hydrogen. So there is a neutral charge in neutral state. That's a recombination. Or in terms of photon, they scatter with the charged particles But once they have only neutral thing, with the neutral things, photon will just pass away, just like we can see the sky, because it's essentially neutral, right? So that's the major thing. And so what we mean by here, we call scalar field as early dark energy means we are, so the terminology means considering the recombination time earlier than that. In a sense, we are calling it as early. So early means earlier than the recombination, roughly speaking. And by introducing this scalar field, we have in mind kind of as a dark energy. So that's the thing. So main idea is that we'd like to introduce some scalar field, so-called early dark energy. So they will really change the early stage. I will show more detail. However, later universe, they will dilute away naturally, much faster than radiation, so that they will not touch any physics in the after recombination, and they will make a change of the evolution of the universe, like a Hubble expansion parameter, for example, so that by changing that, it will affect Hubble parameter, and so that it is more or less higher than Planck observation, which was 68 or something. So it's more than 70. So it's a very consistent with 72 or 3 based on the supernova. That is the main idea. So there are many models for the early dark energy by scalar field, but here, so more specifically to explain Hubble tangent, we are introducing the scalar field, but the potential is like this one. And to explain birefringence, actually we have to introduce some parity violating term. So essentially we have to introduce this one. So essentially this is the one we are playing with, and then this will be making the present Hubble parameter, Hubble constant higher value than the lambda CDM, so that it is consistent with the supernova-based observation.
So the field is a scalar or a pseudoscalar?
Pseudoscalar, I should say, yes, sorry. Because of here, pseudoscalar, sorry. And so let me just first start by the Hubble tangent. So explicitly, the potential is 1 minus cosine potential. And so 1 minus cosine is like this one, from minus, let's say, pi to plus pi, that's a 1 period. If you plug in n equal to 1, it's simply 1 minus cosine cosine. So cosine theta is a 5 over f. Then this one is a theta square, so it's a theta to the 2n power. So if it is the n equal 1, it's a theta square over pi square. It's a mass term. Only n equal to 1, then we get back to this usual action, very light action model in the case of n equal 1 with a mass. So this is, of course, a free parameter given to us. However, in the model that we will work on, n equal to 3 is the what people found most adequate. So if n is bigger than 1, actually the power is 5 to the 2n power. So it's not mass term. So mass is 0. It's really flat. It's a massless. However, of course, there is a wall, so that they are really blocking indefinitely growing field. So that's the difference between our collaborative work before, where the scalar fields are growing without any bound. by still keeping massless and by putting some potential that prohibit too large amplitude, it will confine the amplitude stopping, right? Amplitude cannot grow very, very large. Okay. So field equation is, of course, the dynamics is the Einstein equation by metric variation and the scalar field variation. Okay, that's very simple. And so important quantity is that how much of the energy density of the scalar field and what is the equation of state of that scalar field. W is the, oh my God, I haven't written that down here. W equal to pressure divided by energy density. Okay, so that's the this can be parameterized by this way. For example, so the n equal 1 is the usual one. In that case, it's a massive. So it's a massive case. So W will be 0 if you solve the equation of motion. And the n equal 2 is a 5 to the 4th theory without any mass term. Then it's like a radiation. And if a bigger than 2, then so Wn is becoming larger than 1/3. So as a result, it will decay. So usually decay is like here is 1 plus Wn, as everybody knows. So if Wn equal to 1/3, that's the H3 minus 4. But if it is bigger than that, it's decay faster. So they will dilute away faster than the radiation. So that's the main reason why it will not affect the late universe. They will affect only the early universe. So the solution is essentially, we can divide into two pieces. One is the early dark energy phase. The term is always there. However, the behavior before decoupling and the behavior after decoupling or less scattering will be different. So essentially, early dark energy, since it's earlier, the equation of motion is as so familiar to everybody. So this is like a friction term, Hubble parameter, and the Hubble parameter is if it is a power law behavior, Hubble parameter is 1 over time. So when time is very, very small, very naively, very small, then the friction coefficient is much, much bigger. So it's a friction is dominant compared to any dynamics. So if it's a very large friction, it will not move, or it will be very, very slowly moving until time goes on, so that the friction term is becoming less and less important. Okay. So in that sense, qualitatively, you may expand that in the early time they will not move. Essentially, they will just slowly move in phase.
What is the boundary condition of the field?
Okay, boundary condition is that at the initial stage at the t equal to 0, the scalar field start from at rest. So that's also different from what we have done. We just fixed at the PBN.
So can you repeat? So it is 0?
0. So they start from the phi dot equal to 0. They start from the at rest. Then so it's a different classes actually. Yeah. Okay. So that they will so if it is essentially constant or very slowly roll, constant means cosmological constant in other words, right? So it will just behave like a cosmological constant. And a much later time, then the friction term is negligible. Then it's a kinetic and the potential term. Then it's the oscillation. So numerically, depending on the some the n dependence is there, but this is the z. So as we go that direction, right direction, that's the earlier universe. T goes to zero limit. So in the early universe, they are frozen in some value. So the thing is that we are starting near pi. So near pi over f equal to 3, near 3 at rest. Okay, that's the initial condition. So near 3 at rest, but since friction term is so large, it takes some time that the friction term is less important. Then once it is becoming less important, it's really dynamics and oscillation. But oscillating amplitude becoming smaller because of the dilution, much faster than radiation. So qualitatively, we understand this numerical solution. Okay? And then how can we calculate with this kind of complicated numerical solution? Of course, that's very, so clumsy. So the thing is that considering compared to the Hubble time, or this one oscillation is much faster than the frequency given by this Hubble time. So in that sense, rather than following the time dependence, we'll average out every quantity over this one period. So that's the fluid dynamics. Okay. So this is solution. Once again, here solution. Here is the energy density. Energy density is essentially it's a constant because it's like a cosmological constant. Then they drops out here, as you may see here, CDM. So this is the matter variation. This is radiation, right? Radiation drops faster than matter, so that's why they are meeting. So meeting is at the T equal time. However, this under this potential, scalar field energy will decay faster than this radiation. So it may not be clear, but I guess, for example, this one, I think you can see that it's a little bit fast, the steeper slope, little bit. So that's why we say that this is faster dilute than the radiation. Okay.
So I'm sorry, I have some question in the previous pages.
Mhm.
Shape of the potential, the cosine type is very important. And no, next. Yes, in this, to show the shape of the graph in the right hand side, right and below, shape of the potential is very important. Or any other types of potential is examined?
So my understanding is that massless and the massive may be different. But so n equal 1 is massive, n equal 2 and n equal 3 is a massless. So massive one, n equal 1, behavior is different from n equal 2 and n equal 3. But n equal 2 and n equal 3, so I guess quantitatively only small difference, but qualitatively quite similar behavior.
So when you say that n equal to 3 is optimal, means at least n equal to 3 or I mean,
N equal, really n equal
don't work
3.
and 3 work.
Yeah, 3 is the best in, by some numerical, so because we have many observational data. So not it's not lower bound, but it's actually chosen number. I will show you what people have done. Okay, so that's the solution. And the fluid approximation means rather than following the okay. Okay.
So in the vector solution, how did you fix the mu and alpha? So which is
Yeah, what is
maybe
that?
covering the potential. How did you fix
Okay. So let me just go back to here. So you may say that the number of parameters is essentially V0 and the F. So, I mean, here, instead of these things, we introduce here, in a sense, redundancy, but MF and the F. And so we write it as alpha and the mu, alpha mu. So alpha mu product comes together always. So, but I just chose this notation because some the original paper, this is the way they did, but it's a two parameter, right? With a discrete parameter n, that is the potential, right? Two parameters is mu times alpha and the f. That is a two parameter.
Either alpha F, maybe, or so
Alpha
or alpha
mu.
mu.
Yeah, alpha mu seems to be getting together, at least to me.
Yeah, it's not, you would say that the product alpha mu, there is also an F theta, in other words, or F.
Theta is a dimension, so dimensionless one by the taking phi over f, right? F is the mass scale of the global U1 symmetry grating scale.
So F is fixed.
No, I think I mean in the action, if we are sticking to action, there is an so whatever action mass or scale you have in mind, that's the thing that gives F. But here we are not claiming that this is from action. In that sense, F is free parameter. But
in your analysis, you fixed to some scale.
In not my analysis, but others, I think they chose yes. Let me see. So
Expressed in terms of theta.
oh, where is F? I see.
I mean, everything is expressed
In terms of theta, right? So
Probably I'm missing something. In that plot,
okay.
you said there should be an early epoch of exponential expansion.
There is one.
And where is it in the plot?
However, so here we are assuming that this one is never dominant. Omega compared to, as you can see here, compared to the radiation, they are always subdominant. If we go higher and higher energy, earlier and earlier time, the dark energy is less, I mean, only when they are dominant, it is exponentially growing.
So the equation of state in this plot is either 0 or 1/3.
So let me say, let me say it this way. We have always in the model, I was very sloppy. We have also always some dark matter. This at the given time or scale, this one can be obtained from the lambda CDM value. We know the at the given time how much they are occupying. Similarly, radiation, we know, I mean, the present values and also earlier time, how much they are dominant. And also omega lambda, yeah, okay, so that's the thing. And then essentially this is the new one. And here W for this one can be -1 or whatever, but it's a time dependent. In the two phases, they will behave differently. And the thing is that this one is always very, very subdominant compared to the essentially radiation. Because in the earlier time, it's the radiation is dominant, and this one is quite negligible. So that the scale factor is not exponentially growing, because this is a negligible factor. Essentially, this one, so it's a power behavior, it's a tips they have or something, and then some correction, right? Small correction. That's the effect of this. So that can be seen from here compared to the radiation or matter. As we go Z, it's about 1,000, right? So by this time, it's a radiation dominant year already. So that as you see here, green color radiation is dominant over the metal, but that's even both are much more than this scalar field. Okay. And of course, in the this oscillating phase, we can say that how fast they are dropping, and if depending on the n. But anyway, so qualitative this bigger, faster than so essentially if bigger than 2, faster than radiation. That is important. So they will be more and more negligible as it comes to our present time. So that's why essentially they are not affecting other physical quantities. So fluid approximation, I don't want to go detail. The main thing is just introduce you the ideas. So the main thing is that we, rather than dealing with these really oscillating things, we are averaging out. So averaging here, as you can see here, so these solid lines are real numerical data, and the dotted line is the kind of the fluid approximation. So that it's more or less quite good. It's working very good, right? So, and with that one, I will not explain any further detail. And to really evaluate, we have to do in the background. We have some background, which is very similar to the lambda CDM, but with a modification coming from the additional scalar field. But it's still it is a homogeneous and isotropic. A little bit different from the lambda CDM background metric evolution. Scale factor evolution is a little bit different, as we saw. Under this one, we have all this some fluctuation. That's the source of the power spectrum, right? And we have to do the perturbation. Additional thing is the perturbation of the scalar energy density and the some velocity ones. I will not go detail. So that we have, this is the additional the perturbative things that we have to solve. But if you see this one, to do that, definitely we have to know what kind of metal property it is for the scalar field. So we do need W, which is pressure divided by energy density. In addition to that, like any other perturbation, they do need some sound speed. It's an adiabatic sound speed and also the effective sound speed. Okay, so that's the appearing in the all the equation. So once these are known, then we can solve all the perturbation, and out of this we can get any some quantities. So this is some adiabatic sound speed. This is still this. So here, I did not write down here the source. Still, this is not my work, or this is already, all these things are done by others. So still, again, according to these gentlemen in 2019, with this model, they compared n equal 3 case with a lambda CDM, n equal 2, n equal 3, and n equal infinity. And for my purpose, n equal 3 is important, so I just chose n equal 3 and try to see lambda CDM. So compared to the lambda CDM, we are introducing additional parameter in the theory. For example, the scalar field. So this is the critical value where the lambda, the scalar field phi energy contribution is the maximum. That is the so-called the subscript C, critical means. And at that time, we have also this fraction of the energy, early dark energy. value of this one, when it will be essentially so the about the behavior and also the fraction. So these are of course not needed in the lambda CDM, but to get the in the n equals 3 case, the value is chosen this one, and based on that, if they just calculate the statistical analysis, then the Hubble parameter they got is more than 70 compared to the 68.
Sorry, what's the difference between the number, the first number, and then the second number in parentheses?
First and the second?
I mean, in each entry, there's like, in each.
Ah,
there's
okay.
two numbers.
Okay, I think this is the, okay. I have to recollect my memory. I think this is the maximum value that is consistent marginal value, so-called marginal or that kind of thing. This is the optimized number, and this is the marginal. If it is becoming larger than this one, seems that they start deviating quite much. That's my memory. So in that sense, we may follow this one. Well, I think yes. Okay. So that's what was known. So still, what has been done by those gentlemen were fitting. So here, for example, Hubble parameter, and the Hubble here is a Hubble parameter. If you see that Hubble parameter in terms of AC, and then so this gray colored one, this is what is this? This is, I guess, it's a huge result. This is essentially it's a observation based on the supernova. Okay, so that's the gray area. So you can see that there is some range of parameters that's somehow overlapping with this supernova observation data. You can look at from this one or this one, I mean this one or this one, or you can see also this one. Right? So you can see that. Definitely there are some values which is not good, not just quite working very well here. So even though the central value is not really within the gray area, at least in the statistically they are, you may say that not very, it's better than before with this model. That's what the gentlemen in 2019 they showed in the PRL paper. Okay. Still not my work, our work. So early dark energy to resolve cosmic birefringence. How do you do that? So for we introduce some parity violet term by coupling the pseudoscalar field to the photon field, this FF dual term. And the potential is given this way. And since we do know the results of this Komatsu et al. It's a review paper, and there is also the paper they wrote. So since we do know their results, we are interested in only n equals 3. Okay, so once again, by introducing this Chern-Simon term, since they are breaking the parity, right-hand polarization and the left-hand polarization will propagate in the different speed, so linear polarization will be rotating. So that's the one thing. And as a result, we may have some cross-relation power spectrum. So what I mean by that is that let's not go to any detail. So essentially, if we think about so writing down everything in terms of spherical harmonics, vector tensor spherical harmonics, because tensor 2 quantity, then we may say that electric field and the magnetic field, how the E mode and the B modes are opposite parity. So EE and also the let's say B is odd. So but odd is even again. So EE and the BB is parity even, but EB or the T is also parity even, but the B is parity odd. So TB, those things will be parity odd. So if they are not absent from the beginning, they will never be produced in the parity invariant theory. But the main thing is that this one will be produced as they are propagating. That's the way they can measure. So there are some more details, but maybe better not to go detail. So, so the essential thing is that the EB power spectrum is generated only the parity violet through the parity violating terms. Okay, that's the main message. So with these things, they means here. I didn't write who are they. Okay, here is the day. In 2023, so rather recent. 2023, they showed that by choosing the parameter properly here, important parameter is what is the important parameter? There is there must be some the Chon-Simon coupling constant. That is the most important thing. So that's the G. So I think somehow I lost where is that parameter G. Maybe they chose some parameter G value. Then roughly what they have done is that the important thing is the coupling constant G, which is the coupling constant of the phi times FF dual term. That parameter they just first fixed, then they just let all others varying, and they optimize like a chi-square, let's say. And then they found that these values are the most proper things. So most well-fitting with all the known observations. So the thing is, the observation is these two things, or the blue and the green color, but and this black color lines are the data. So data is still with the large error bars, but we may say that blue or green color does not fit well with the observational data. But anyway, this is the one they analyze and this way in their paper. So conclusion of these gentlemen is that first they chose G value, the coupling of the parity violating Chon-Simon term with this value. Then they found because they chose that value because of all this analysis, the conclusion is that, and with n equals 3, by comparing with the observational data, it does not fit well. That's their conclusion. Okay. But here the thing is that they by varying and they chose the best value of the this coupling, early dark energy model, parity violating coupling. Then after choosing the value, they fixed all the other values with a previously known value. Then by doing that, then the EB power spectrum does not agree. Here, this is the EB data, and they are first is not zero, right? There's in the 3 sigma level, But for the detail of the angular the size dependence, they cannot really fit well with the N=3 model. Once they fix with these values, and then does not fit well. Okay. So what we have done is that unlike so this is the few pages what we have done is essentially why don't we simultaneously fit the parameters, not fixing all the 9 or 10 parameters, but having only the G values. But all these things we fit together simultaneously. Looks like very small minor difference, right? However, what we found is that by doing that, by kind of relaxing that parameter, then it seems to be fitting quite well consistently with the EV power spectrum in the cosmic biodifferentials. That's the result. So once again, this is the known results. I mean, they always chose these values and then plotted or chose the coupling constant of the Chern-Simons term. And of course, even the Chern-Simons term depend on what kind of values you chose. But in all the known papers, they always choose in the two group, Pauling et al. And Eskid et al. They always chose either the Pauling fix these values, or Eskid fix these values, and then plot the GEDE. That's the way they got the GEDE. But we just vary simultaneously.
Understand. So you have these 10 parameters, 4 plus 6. So we are saying that the other people are fixing 6 parameters and just doing them.
Right.
Only the 4.
Or let's say, so 10 is rough, if I remember correctly, 1 plus 9, they fixed 9 parameters with those values, or maybe, and then under that, they chose the remaining 1 parameter GEDE, the coupling. So that means the conclusion is that with these values and all the values chosen this one in the Pauling et al. Or later one, the Eskil with these values, and then this with this one, then it does not describe EV power spectrum well.
So the bottom line is that if you have 10 parameters, you should analyze 10-dimensional parameter space.
Right. That's yes.
And then just
Then
compare the chi-square per number of degrees of freedom. And
right.
see.
That's what we did. Yes. Yeah. Essentially, so it looks like a minor difference, right?
Well, no, the plot that you're showing is exactly showing the opposite. Because if you fix the other parameters in a different way, G becomes different.
That's right.
So,
But anyway, that's on the two different
significant.
paper. Yeah.
yeah, see, exactly.
Right. So the green color is the 2023 those gentlemen's one, and this one is what we did. Okay. So as you can see there, so what we did was simultaneously changing all the parameters. Then looks like better fitting, right? So it looks like consistent, which can be seen even with the chi-square values. Chi-square is quite much reduced compared to the previous values. Okay, so the message is very simple.
If you have 10 parameters, you're supposed to change all of them. To vary
Right.
all of them.
Yeah, that is true. So I mean, to understand better, we try to understand how each parameters are affecting CMB EV power spectrum. So since it's too little, I just made it very larger. So green colors parameter change. Well, it doesn't change very much, right?
So can you explain exactly what is in the
Okay,
green
this is angular momentum. So the scale,
small
and this is a CEV.
case?
And so here, So here, what we are doing is that we are changing F ED or here NS or anything. And here the data is that the green color line is the best fit data. And then we just try to increase 10%. And also we just decrease 10%. So some larger value of the NS, optimal value is a solid curve.
Sorry, I'm a bit confused. In all these 9 plots, the dots they don't seem to be the same points.
Okay. Okay, so, okay. Let me explain one by one. Here, if I choose N as the best fit value, then what I got is the, here the, so I got this solid line curve.
What are the data? The data.
This is the EV power spectrum. And this is angular momentum, always,
So the
everything.
dots are supposed to be the data.
Okay, data is actually this one.
This one. So yeah, no.
Mhm. So question is how to get the plot. But here, the main message is how sensitive this power spectrum, cross power spectrum on each parameters. So here the orange color is bigger, 10% bigger than this best fit parameter NS. And the green color is somewhat smaller than the best fitting parameter, 10%.
So the quantity that is the same in all the 9 plots is the solid curve.
Right,
The solid curve is
Yeah.
the best fit.
that's right. That's
And then, for instance, in the plot in the center, when you change a yes, minus 10%, plus 10%, you see the green and the.
green or the orange, yes. So here, as you see, most of the parameters, they do not change very much. However, there are some parameters which drastically changes, which I wrote as a red color. So ZC, also it is red shift in the related spectrum where the energy density is the
Anything
maximum.
related to CP violation, to parity violation will change. And things that are not supposed to be, this is the best fit of an effect that violates parity. So of course, this will be very sensitive to anything that is determines the amount of parity violation.
While others
The other
are,
parameters.
good. That's, I mean, okay, thank you. That's a very, I mean, much better way to describe. So here, that's the thing. If you have any oscillating curve, what we do need is the amplitude and the phase. But the amplitude, the little bit changes may not be that significantly important, but the phase difference is quite different. Here, in a sense, so phase is drastically changing. As you can see here, green color and orange color compared to this optimal value is really drastically changing. Okay. And other plot is, this is to support our analysis and to really understand what's going on. So we are fitting all the parameters here. Based on that, if we can evaluate H0, then the maximum is much, so it's really around the 72 or something. And also GEDE is also this range. Okay. So this is again with this non-zero and some specific magnitude of CP violating parameters. We can not only explain the EV power spectrum, but also we can still, this is consistent with, make it more consistent with or make it less stringent for the Hubble tangent. because it is a little bit bigger than, so closer to 22, 72. So again, here in the many things here, essentially thing is that this is a new parameter. And so all together, we are varying all together. And then based on that, if we calculate the Hubble parameter, then it's about 72. And this is just two-dimensional plot. This is one-dimensional line shape. So I don't want to explain these things. This is really H0. So that 70, 72, that's the value. And depending on the parameters, it's more consistent with the supernova data. And also GED is definitely it's a non-zero, it's a highly preferred, as you can see here.
What is omega CH squared?
Omega CD, because the cold dark matter,
This is just
yeah. So capital omega and the small omega is, I guess, with some normalization or some essentially it's a cold dark matter contribution. Okay, so essentially that's it. So that's what we did. What we have done is very simple. So in summary, I just say that with a little bit different analysis, we can see that N=3 early dark energy model can simultaneously explain the cosmic birefringence and also Hubble tangent. So that's the main message. Okay, that's it. Thank you.
So for N=3, what's the behavior of octable N? And what's the behavior of the double N?
WN.
Yes. Or cosmic time.
Okay, this is the W. So WN or W5. So here, this is the most general one, but we also define in terms of WN with this one. This N is the power of the thing, and this is the really right parameter. And I don't think I have a plot of this itself. But since this is essentially omega is the pressure over rho, maybe including part of this one, but I do not know. But at least in the two regions, this region and this oscillating region, we can evaluate that one somewhat easily. That's easy. So roughly speaking, in the slow roll region, essentially it's frozen. So let me see. In the very early time, so A is quite smaller than A sub C. So this is very large number. Is that right? I think this may be, I think. So this one is negligible. So the A to the this power and the WN, then I think what I want to say is that W5 goes to the -1 in the this region, and the oscillating one, there must be something also here. Oh, here we go. For A equals to 0, W5 goes to -1 independent of N. But in the oscillating phase, W5 goes to the WN.
WN is
WN is given by this one, and this N is the power of the.
so 3 minus 1 divided by 3 plus 1.
3 minus 1 divided by 3 plus 1. If it is a 3, yeah. So here I wrote, yeah. Wn is bigger than 1/3. That's more important, right?
So it's 1/2 or not? No, I don't understand.
3, 2,
minus one,
4,
3
half.
1/2, which is larger than 1/3.
I see. Okay, good. Okay. So Wn equal to half is bigger than 1/3. And that means it's a faster than radiation. What is the power? Maybe 5 or something, or I don't know. Half. So it's a half. So 8 and 9/2. So 8 to minus 4.5. Seems that. Okay. That's the decay of the energy density.
Enough late time so we can simply neglect that five.
Enough later time. Okay,
So, yeah, later time.
that's right. So they are dilating away with this one. So it's faster than radiation. And right. So that means present time radiation is 10 minus 5 or something. So this one is much smaller than that. Right?
So the effect of rotation of the polarization is supposed to happen between recombination and this moment when
Even present time, right?
so when the scalar field disappears.
It never disappears. It should be there, right? But it's a small amplitude.
So my understanding is that if W becomes bigger, larger than 1/3, it will be diluted away. So
Diluted away, but does not mean that it is 0.
yeah, but eventually nowadays it is 0 or it is negligible.
Quite small, negligible, right? But it's not 0. And so what I wanted to say is that, how should I say? Let me see. Here, the angle essentially depends on the phi values. So if we just choose this at the present value, and if it is 0, it's a very good approximation, right? But it's still some number. So it's still, they are contributing to the rotation, but less and less, I guess, something like that.
So this effect is clear, but I don't understand. So it's not intuitive to me, I guess, that you can change the Hubble constant if the contribution of the additional term is always not subtle. I mean,
Could you repeat?
so the equation of state of the universe, so globally, is either dominated by matter or radiation. And then you have this contribution of the scalar field, which is subtle.
Right.
Always. But Hubble constant is a global effect. So if you have a subdominant term, it should affect small. So the expansion history of the universe should not be much affected.
Right.
It's also true that probably the difference, the Hubble discrepancy is a small amount.
Right.
So you are just changing by, I don't know,
Yeah.
probably 10% or 7%.
Not much, yes. So for example, if you look at some other guys' previous work, for example, the parameters, it's not really big difference, right? And by just introducing the early dark energy through these kind of things, without changing very much, so they are really affecting H0 just a little bit. But to do that, what you are doing is, to do that, you have to do also the also there's some perturbation, and then they are so through these things change. So the presence of this one will be changing the sound speed and so of the scalar fields and etc. So those effects eventually contribute to the Hubble parameter. Of course, it's a subdominant.
The effect is dramatic on the parity violating term, but on the global expansion of the universe should be very small. So anyway, it's enough.
Right. So the important thing is that I myself try to search out all the, let's say, Horndeski models. When what is his name? What is that very aggressive gentleman in the island? Owen. When Owen is here, we just worked on that. Try to see whether any single Horndeski model will be toward the direction to reduce the tangent. Conclusion is that no. So the interesting thing is that this model is helping. So the introducing this parameters, so this interaction will contribute in reducing the tangent. That is the important message. Randomly, many models that we tried were against that.
I think that you can continue the discussion after closing the session officially.
Okay. Okay, then officially over, then I can answer.
Yeah. Okay. Yeah. Thank people again.
Thank you. Okay, what is the question?
So I was just going to ask about the potential that you write out for the axiom. So I know that from string theory you can get these from like piezo and some knobs or something like that where you and in principle. So one question is, in principle you should get the power of like arbitrary n. So one issue could be, how do you suppress like any component in and another question, which I guess is partially answered, is whether, so that's from string theory, but whether there's any other modified gravity or any other type of scenario where you would be like this.
For the fourth equation, I do not know the comparing n equal 1, 2, 3, etc. And here we simply chose, well, people also simply chose n.